So I'm going to do a few slides just to kind of set the context, and then we will show some live demo. So a couple of words on SonarSource. So SonarSource is a company that was created 13 years ago. We have now almost 300 employees across 4 locations. Geneva is a headquarter in Switzerland. We have offices in France, in Germany, in the Ruhr area, and in Austin, Texas. We do what we call clean code on 29 languages now, including, of course, C, C++, Java, Python, but also legacy languages like such as COBOL. And we also do infrastructure as code. Lots and lots and lots of companies use the product. It's really massively adopted. The base is open source for SonarCube, and it's free for open source project for Sonar Cloud. I think we distribute about 75% of the code that we write in open source, so we really have a strong commitment to open source. Let me talk a little bit about what we call the power of clean code, which is, I think you probably realize as a developer, software engineers, that if we had a world where the code is clean, and when we mean clean, we mean it's consistent, it's easy to read, it's bug-free. I'm talking about technical bug. It doesn't have vulnerabilities. It has a simple enough style, and like we write it in a consistent way. I think the life of developers would be much better, which is you would be able to read somebody else's code and kind of understand it easily. You would be probably willing to change other people's code. When you make a change, you wouldn't have to worry too much whether you broke something elsewhere, because the code is so tangled that you don't really know if you change something here, whether it's not going to have impact elsewhere. So if you have what we call clean code, you would do less rework, most likely less maintenance, or at least when you do maintenance, it would go quicker. So you could probably spend more time on really interesting problems for the business, innovation, on really solving good problems. So this is really what we try to do. Another thing is that we tend to forget it, but developers spend, I don't know, a lot of time in code. And when it's crap, it's basically your work environment is bad. Maybe you have the best computer, you have the best office, etc., but if every time you open a file, it's a nightmare, it's not a good work environment for a developer. And also, of course, if you have clean code, you reduce your risks when you go to production as an organization, which is you shouldn't have an application that keeps crashing, and you should not be too open to vulnerability risks. So all in all, when we are talking about clean code, we are actually talking about the quality of the work that developers do, which is the output. If you do clean code, the output of your work is kind of good. Let's put it the other way around. If your code is not clean, this is not a good job. For anybody who has tried to engage on cleaning the code, I'm sure you have hit some major roadblocks, which is, this is always done late in the process. I don't know how the process works in your organization. Generally, it's like, okay, once we have finished everything, once we have tested everything, we are going to review whether we should pay back a little bit of technical debt. It's far too late. It's never going to happen. You are only going to do, what do we call that, lip service, like very cosmetic changes, nothing fundamental. It's far too late. When you have auditors who come to developers and to say, hey, this is not good practice, you should fix it, you should fix that. Also, there is a lot of pushback from developers who like that somebody else comes to explain to you that you didn't do a good job, especially when this person is not technical, it doesn't really work. So overall, in the process as we see them in general in organization, there is a big lack of ownership. And at the end of the day, we at SonarSource, we believe that the standard, the quality of the code, the security of the code, that should belong to development teams, not to anybody else in the organization. Another thing which makes it super difficult is that when you start to think about the standard of the code you want to reach, very often you start to do cuisine, which is you start to say, okay, well, this application is legacy, so we should be more we should be more open for bad code. This is a new application. We should be like, it should be 100% clean. Or here it's a junior team. We cannot have the same expectation. Here it's a senior team. Well, they probably know what they are doing. So we do a lot of cuisine. We start to make it super complex in the organization. And if you make this kind of thing super complex, it's going to be difficult to have a wide adoption. And finally, the thing which we see everywhere, I mean, we saw everywhere, is there is no quality gate, which is there is nobody in organization who has the power to say, we are not going to release. The code is not good enough. This is not the standard we want to deliver at, so pushing back. I mean, maybe some people have tried, but I don't think they could succeed consistently. So all in all, this is no fun. I'm not going to tell you in this presentation that code quality, code review, etc. is fun. Not what I'm going to tell you. But here, when you approach it this way with all these challenges, this is definitely no fun at all. It should be, code quality should just be part of the work as, hey, this is the kind of standard I'm going to deliver up to. Okay, so the way we look at this problem at SonarSource is super simple, actually. What we consider is we consider that if you don't see that your clean code is actually similar to a water leak problem, it's going to be difficult to have a sustainable approach. Let me try to explain this. Tell me, if you have okay, that's a big one, but if you have a small water leak at home, what do you do first? What's the first thing you are going to do? Okay. Sure. That's very temporary, right? The bucket. Yeah, sure. Sell the house. Okay, fine. Any serious answer here? Fix the leak, right? Turn off the water. Anything else you do, anything else is useless or just delaying the problem. Like, if you don't fix the leak, you're going to end up with a lot of water on the floor. So if you think about clean code, it's the same thing, which is when I don't know why, intuitively, when we look at an application, when we see that the quality is not good, the first thing we want to do is we want to fix stuff. It's like mopping the floor. And when actually you have still, I don't know, 5, 10, 100, 200, 2,000 developers who keep adding, changing code the same way they have always done it, which is injecting new problem, etc. So basically, whenever you start to look at, it's like mopping the floor when every, how do you call it, every pipe is open on just pushing more water on the floor. So basically, it's kind of useless. It's a battle you are never going to win. So the way we approach it is, and this is what we developed this kind of methodology internally at SonarSource. I mean, we tried it. We tried and failed and having clean code for many years. And then we started to approach it this way, super simple. It's going to sound simplistic to you, but I can tell you it's extremely powerful. So the first rule is there will be a quality gate, which is if if the quality gate is red, sorry, if the quality gate is not green, the code is not promoted. And this is automatic, and it's never challenged. And the way we make it not challengeable is we only look in this quality gate at new code. The code that was added, the code that was changed. So basically, any code that has been touched by a developer during this change, and the size of the change can be anything you choose it to be. It can be a pull request, it can be on a day, or 2 days, a period, a release. You choose. If it's not green, it doesn't get promoted. So basically, in other words, what we are saying is that if you inject new issues, you are not going to be able to release the application. Simple? Fair enough? Okay, very good. Okay, so now what we are going to do is we are going to show how we actually are able to sustain this. We used to call it water leak management, but we now chose to call it clean as you code. Sorry, I forgot a super important point, sorry about that. And by the way, because software is soft, and we keep changing software, I mean, I don't know how much time you spend to write entirely new features or to change existing feature, but I would think that 90% of the time, or maybe 90% of people in this room, change existing code, and do not write so much new code or so much new features. Because we keep changing existing features, actually this is going to propagate, the clean code is going to propagate through the software. Industry numbers says that organizations change about 20% of their code base every year. So basically it means that by applying this after 1 year, 20% of your source code is going to be clean. After 2 years, it's not going to be 40% because there will be some overlap with the first year. It might be 30, 35%, whatever. After 5 years, it's certainly going to be something like 40 to 50%, which is really great, which is with no effort, no specific effort, just making sure that what you touch, when you touch code, when you add code, you don't inject problems. After 5 years, you are going to have a good chunk of your code, which is clean. And the good news is that that part of the code is the part of the code that has been changed. It means that the rest of the code has actually not been changed. So it's kind of probably the part of the code which is, I would say, a bit less risky, or which requires less to be clean in terms of priority. It's quite nice to start this way. And now, for real, I'm going to hand over to Geoffray, who is going to do a demo.
Hello, everyone. Oh, great, it's working. So that's my turn now. So first, I wanted to start with a bit of C++ code, because I was expecting you might like this. So I want to give you a little glimpse of what sort of issue we raise on code. That's tiny, of course, because we've got just a few rules. But still, I thought you might like it. So first, I wanted to talk about performance, because actually often like code quality is about bug, is about code smells, but also you could say, okay, what about performance? So this one will not surprise many people here. Yes, of course, when you write a Lambda and that you're going to use this Lambda right away with an algorithm, or because you will call it, actually it is totally safe because you know that no variable will get out of scope to use the capture that you're going to use to do it by reference. So this is the sort of issue that we can spot. If you don't do that, actually you will get slowdown because of copy. You will get extra memory allocated for nothing. And this issue is nice because also it can be quick fixed in your IDE. And so we'll see here. So we have here a vector, and we're doing a transformation on this vector thanks to this lambda here, which captures the vector here. And so what happens is basically what you want to do here is to have this vector by reference so that you're not copying uselessly this vector. That was the first one. Then also something which is overlooked sometimes with tools taking care of C++ code is some sort of security. For instance, here we're talking about OpenSSL, okay? So security can be a quite technical matter, and it's not like every single developer always masters all the concept of this. So you might be led actually to use some cipher algorithms that are just not safe anymore, and that are really notoriously known not to be safe. So for instance, we will tag all algorithms that you might use on OpenSSL that are not safe by today's standards, okay? And this is very serious, as you know, because you can really totally endanger your business by using these sort of things, because if hackers manage to actually break your encryption, you can really leak personal data of your clients and do all sorts of crazy things that you wouldn't like to happen. So in that case, all these cipher algorithms, you don't want to use them, and mostly something that you would like to use is such an algorithm. So we do this for OpenSSL, we do this for Botan, we do this for Crypto++, and we take care not only of the algorithms, but also of the encryption, of the length of the keys, of the padding schemes, and all that. We check all sorts of things for you to be sure that you're not endangering your encryption. Another rule which is quite nice is this one. Many people would actually thought, okay, I have this very sensitive data in the memory of my process. And I know that hackers can be a bit tricky and manage to actually access some parts of the memory of my process. And so I will just erase this sensitive data. If this sensitive data is actually a password, for instance. So what I'm going to do, okay, I'm just going to write spaces all over the area of memory that had my password in there. That's great. I will do this also for this other thing. So one is in a variable which is on the stack, and the other one is on the heap. But in that case, both of them will actually die at the end of this function. But what happens here is that actually your compiler is smart. And when you optimize this code, the compiler will say, hey, I'm just writing something here that will never be read. So I will not write it. So your password is still in memory, at least for the one which is on the heap. For both, actually. So yeah, in that case, what you need to do is to use the memsetS function, which is secured, which cannot be optimized away. This one also, yes? Okay. Sorry? How do you know it's the password, not another variable? What do you mean it's not another variable? That line where it's another S. Yes. Maybe, how do you raise the warning that you should be putting an _S there rather than actually that was... You just need to understand, and the analyzer does that, is that actually by the end of the scope, you're not accessing this variable to read the content. Okay, so you're just saying it's an unused variable. It's not unused, it's just the content that you've been writing using memset is unused. Okay. And at this point, you might expect that the person was trying actually to clear the memory. And so we're just saying, oh, if you intend to clear the memory, maybe you should use this. Okay, so you're not trying to detect this password. No. Okay, so now this argument evaluation order should not be relied on. You might know that, and I'm sure you do, that the order of evaluation of the argument that you pass in a function call is not specified. It's even worse than that if we go into the details, but let's not. The thing is that we can catch this expression that looks like they might actually have a dependency on this sort of order of evaluation of arguments. This is something, in that case, that looks quite obvious, but sometimes you might actually miss this sort of stuff. And so I think that makes it quite valuable because it can slip through unit tests and you can end up in a sort of nightmare with really bad things happening. And I think that's it for the little rules that I wanted to show to you. And right now, what I would like to do is to show you a little bit how it's like when it's in action. So we are talking about our solution, and our solution starts first in the IDE. So in the IDE, we have this linter that will catch many issues, including the ones I showed you, but actually more than 500 possible issues that we can detect. And I would like just to do a little bit of hands-on with you. So what I have here is a little toy code. I have some checks, and I have, let's call it this class, which is a RAII cleaner. And when it's distracted, it will actually call all this cleanup code, right? And so right now, if I look, I have some issues on this code. For instance, here, I'm being told, ensure that this destructor is exception-free, okay, which is, let's say, a classic of C++, right? So, oh yeah, it's not exception-free because cleanup is not exception-free. Okay, maybe I should put it exception-free. So I do that, and what happens then is that I'm being told, remove this new except clause on the function declaration as it can throw. Oh, really, it can throw, does it? So I do to do cleanup. And, oh, yes, this thing can throw here. If I go back to the definition of critical check, oh, yeah, it throws an exception. So we detected that actually, this can throw. So I cannot just change the definition like this. Probably I should actually just catch the exception. So I prepared a little bit. So I have something to handle this here. So I'm just going to try and catch instead of just doing the cleanup. Here, up. Let's do this here. And so what now? What about now? So what about now is that, so can I say now that it's false? Probably. So what happens here? Oh, ClunkTidy invited itself to the party. It was not in the plan. So SonarLint says, I have probably a quick fix for that. So what is, come on, come back. Yep. So it sees that actually this derived expression here is dead code. This catch is dead code because there is a base exception here. And if derived exception is thrown, it will be caught here in this catch clause. So I have for this a quick fix. Ooh, that was not what I was meaning to do. Okay, let's do it like that. And I can, so you see, I have 3 possible quick fixes for that. So either I can move this part here after the more specific handler, or before the more generic handler, or remove it altogether. Let's pick this one. And so now I'm reordered in such a way that there is no dead code, and I will catch the derived exception first. So that's more or less this sort of thing that we have here in SonarLint. And you will just say, well, that's just a linter with some quick fixes. It already exists somehow, yes. We take good care of all these rules and all that. That's not the only thing. Of course, we have all these rules. We have also, what I didn't show here is, which is very nice, we have very nice descriptions of the rules here, very clear and concise. You have non-compliant code and you have compliant code. So within your IDE, you can really understand what's the matter. But the thing is that if you stop here, yes, that's just a full, there is nothing really big news here. So I said I wanted to talk about the solution. So we were in the idea, what happens next? So next, Sorry guys, it seems that, oh, okay, that was not exactly right. I'm sorry for that. Okay, so what happened next is this. So you're the developer, you did your stuff in your IDE, and now, well, you open a pull request, right? So you do that. You have someone taking care of the review, and everything is going fine. You have some feedback, you're including the feedback, and all that, and by the end, you arrive at some point where the code is stable, you agree with your reviewer, and you have this happening, this magic, which is the code is being analyzed by SonarCube, and it's coming back here. And here, for instance, you can see there were a few code smells, and they got fixed. But actually, what you get, if you go on SonarCube, is here. You have this pull request, and you will see here, is there anything that requires some attention, right? So it's passed, so it looks okay as your pull request, There's no new bug, no new vulnerability, and no new code smell. You will note the word new because this is actually only your new code. So even if your base branch had some issues, this is considering only the change and the new code. So it's not bothering you with legacy. You have some ratings here for reliability, security, and all that. And so it seems that everything is good here. Your pull request looks in good shape. So what I would like to show to you next, basically, is when you have some issues, this is how it looks like. So you can see all your issues by type of issues, the bug, the vulnerabilities. You can filter by severity of your issues and all sorts of criterion, right? And when you have an issue here, so if you open it, so sorry for this. This is Java code, but we had to change minor things here. You would see the issue type. You can have a code smell, all sorts of issues, how severe it is. And then this is where the collaboration kicks in as well, because at this point, you're not on your ID anymore. You're with a team, right? So here you have an issue that you can resolve as fixed because you think the issue is fixed, even if it's still flagged. You can say that's a false positive, but trust me, that doesn't happen that often. And you can resolve it as one fix because you think it's not relevant in that context, right? And you can assign, of course, the issue to someone else because it might be for a specific topic, for instance, that you know that someone is more the expert about, for instance, or that it was done for a commit for someone else, or these sort of things. So this is really how the experience you have once this analysis is available on SonarCube or on Sonar Cloud. This is what you see. So at this point, we said that we were really like after the pull request. And so the pull request can be merged to master. And then what happens is that basically you have your branch, you have your master branch, and you're at this point. And you say, OK, now it's time to release. Can we release? So what you see here is still about new code. So you see your quality gate is that, OK, all the new code that was inserted there looks good. There's no big problem in this new code. And as we said, we're focusing on new code. Maybe you might have some other problems on legacy code, but the application's been there for ages. It's been working, no big problems, or maybe but they are like from the past and they are registered already. We are focusing on the present and on the future. Everything looks fine. You have all these ratings that you can configure. And after that, you can also configure what are the levels that are allowed to pass this quality gate, to go back to what Oli was saying. And basically, at this point, you're sure that everything that was added to your software and that's going to be released has the quality that you're expecting, is as clean as you think, because it's not only about quality. Finally, I would like to show you this thing, which is basically the quality profile, because you might think, okay, but there's plenty of rules, all that. And of course, we offer many, many rules, more than 500 in different categories. And of course, that's very important for you to find out the set of rules that make sense for you. We work really actively to have a default set that we call Sonar Way, which is really good out of the box for many situations. But I know you guys have really strong and fair opinions on many things about C++, and that's very important that you can tailor it to your needs. So, for instance, in that case, we actually have SonarWay, which is the built-in, and we add even more, because what you see here is our instance on which we work, and we actually submit our code to our own products, which I guess makes total sense to you. So that's it. That's what I wanted to show you. And now I will give the mic back.
Yeah. So, thanks. Very good. So, quick wrap up, and then we'll take questions. So, just to give you an idea of the extent we cover C++, we have more than 500 rules. We also do quick fixes, as Geoffray showed. Which is we offer automatic resolution for our problem. We cover a few standards. We have rules which are specific for C++ 20. And if I go back one level up, from what we showed today, so super powerful to keep clean code or to clean code, basically. It will help you, it will help the whole team, it will help the organization to do a better job, to spend less time in reworking, maintenance, and more time into delivering value. The way we propose to approach this is this clean as you code, which is you as a developer, as a development team, you focus only on the new code. The rest is past, and focusing on the new code enables you to do a good job and to also remediate the past, as your changes are going to spread through the software. If you think about what Geoffray showed you, there are really two parts in Sonar. One is really the part which is in the IDE, which is as you code, you interact with, you write code, you change code, and you get a chance to not inject problem, not add problems. This is kind of optimal. This is where you want to do it, which is not introduce a problem. If you introduce a problem, when you create a pull request, you get a chance. I mean, the person who is going to review gets a chance to catch the problem. We provide a way to do an educated decision on merging or not the pull request. And then the rest is really for the team, for the organization, which is to say, there is this quality gate, which is going to catch everything that has passed ID time or pull request time. And then everything else is about how to navigate in your project, review what you have. You can do a lot of investigation, see code. You can do configuration. You can choose your rule set to agree within the team. But this is kind of, I would say, it's more like the glue. The main things are every time you want to promote the code, you have an objective review which tells you how you are doing. Probably if you are not using Sonar already, the best way to start is with SonarLint, which you will find in the marketplace of most IDEs, not to say all IDEs. And it's by the way, it's a free product. And that's it. And happy to take any questions you may have.
You've shown that you can integrate this tool with your pull request.
Yes.
But what kind of platform are supported, like Jenkins or Travis?
So we integrate with the what we call the four major DevOps platforms, which are GitHub, GitLab, Bitbucket, on Azure DevOps, in terms of full platform. But we also provide like a zero configuration analysis in tools like Jenkins, for example, and I think also Circle CI. I think we do on Circle CI and some others. But the most used ones we are integrated with.
So we have like three options locally to the ID, CI/CD tools like Jenkins, and pull request tools like GitHub.
Yeah, I see what you mean. You can block, you can fail builds, which is what you are talking about when you are talking Jenkins. You can do that. Technically, you can do it. It's not really something we are big fans of, which is it always creates debates on challenges. We are much more into, okay, you do your own cleanup by yourself in your IDE. You have all the tooling. You have like instant feedback on this, and what you should push, what you push should already be good. And then someone is going to do the pull request review. Blocking automatically on failing builds, we have done it. I mean, we have used that way at SonarSource internally, and it's not the best. But you can do it if you want to. You had a question, yeah?
Can you integrate SonarLint with CMake and have it fail
Are you asking this question because you know I won't be able to answer?
Can you say again, please? Can you integrate C-Lion with?
No, actually, I can answer it after thinking about it. I think the way we approach this is, okay, you can do integration because we have APIs, etc. But we try to more provide like a product, which is SonarLint this is an add-on in your IDE, and we try to integrate with the IDE and to provide the best experience. It's not like a command line tool that you can add wherever you want to. So slight nuance. We used to have this approach, which is, hey, here are all the features that we provide, and you can then do your own integration. We are more into like, we think this is how it should work.
Maybe I can add, I mean, CMake projects are supported in Visual Studio, VS Code, and C-Lion, for instance.
Other questions? If you guys don't have questions, I will ask you questions. So. No other questions? So who is using Sonar already? Okay. Oh, that's great. Thanks, Phil. So who is going to use Sonar? Who is going to try Sonar after this talk? Okay. Not bad. Thank you, guys.